Lava plains. So this is the dumbest form of volcanism, which is just the crust became thin and fully melted. And then it was flat and melty. Okay. So it's like you left a piece of chocolate on the top of your oven while you were cooking something else, and it just melted. The chocolate being the lithosphere, the hotness being the hotness of the stove, which is this represented by the hotness of the planet, and then the top just melting. And then, of course, after a little while, it freezes again because space is cold. So space is cold, inside a planet is hot. Okay? Okay. How's it going? Okay, I'm gonna unplug this if that's okay. We have some really cool slides today. They're not present.
Would you like the projector on right now?
Yes, please. Okay, let me do a clicker question, but you can't see the clicker question. How about that? We'll keep going. Okay, lithosphere. The outer, cool, hard layer of a planet. Which planet should have the thickest lithosphere in terms of percentage of the planet's crust mantle? Is it A, a large planet, B, a small planet, C, the lithosphere should always stay the same percentage of a planet's radius, D, lithosphere thickness does not depend on size? Let me know when you're ready. Okay, is it A? You know what the answers or the question?
All the above.
That's why we.
Oh, B. What's that? Oh, okay. Lithosphere. What's a lithosphere? The outer, cool, hard layer of a planet. Okay, good. Which planet should have the thickest lithosphere in terms of percentage of the planet's mantle and crust? Is it A, a large planet, B, a small planet, C, that lithosphere should always be the same percentage, or D, the lithosphere does not depend on size? Okay. Thank you. Yeah. Oh, it's okay. We do that often. It's okay. We're gonna be fine. We're gonna be fine. All right. Let's go to PPT. Thank you.
Yeah, of course.
Appreciate it.
Okay.
Oh God. Oh dear Lord.
I think I might like.
Wait, where's the Zoom? Did the Zoom drop? Helpful. Super helpful. It's not showing anything. All right. All right, folks, show me your slide choices here. Okay. All right. Who wants to defend their answer? Yeah.
So it's a small planet. I chose B, by the way. The small planet has big cooler longer, therefore more experience with cooler. So therefore it's gonna have the bigger
Right, because the outer hard cool layer is what defines lithosphere. So this is not correct. This is the opposite of the answer. And this one is a trick. Okay. Okay, so it's small planet. So we talked about the role of size here, and we showed the distribution of sizes. This is to scale with respect to one another. So Earth and Venus are very comparable in size. That's something that we want to drill into our head, because notice that Mars is significantly smaller, and it is almost all lithosphere. So it's potentially not surprising that despite it showing features of ancient water, of volcanism, of tectonics, all of those features, again, are ancient, over 3 billion years old. The surface has probably been dead for much, much longer, right? So certain regions are 4 billion years old, whereas the place that you find the oldest crust on Earth is? Correct. Where do you find the youngest crust on Earth? Yeah, the ocean. The ocean in general is the youngest crust on Earth. You can find it in a lot of places. You can find it in Hawaii. Hawaii has a brand new mountain. And you can also find it in the middle of the Atlantic. But you have to swim to the bottom of the ocean, so it's not easy. Okay. All right. What happened to Mercury? We don't know yet. It's a weird one. The moon is lithosphere all the way down. Okay. All right. So we talked about this really briefly, and I'm going to give you a lecture tutorial to talk about it. It's going to get our brains moving today. Planets have three basic fundamental properties. Size. What does the size tell you about? Tells you about what it's made of, sure. What does it tell you about? It tells you what it's made of. Let's say I know I'm going to limit it to terrestrial planets, the stuff that's made of rocks. So yeah, so I have the density. Let's assume that I know that, and I tell you I have a planet that's 5 times larger than the Earth, but it's made of rocks. What do you know about it? That's what?
Probably hotter.
Hotter, right? Because we said, what did we say about the cooling rate? Proportional to the radius, or it depends on how we talk about cooling, right? So is it a rate, or is it the time it takes to cool? So the time it takes for something to cool down is proportional to the size. So the potato and the pea, which one cools faster? Smaller one. Right? So I think that's what you meant. Yeah. Good. So size, mass, and radius does tell us something really important. First, it tells us density, and then it tells us whether or not the thing is cold. What does distance tell us? Yes, exactly right. So I always think about this one as the analogy of there's a fire, and I stand closer to the fire, I'm warmer. I stand farther from the fire, I'm colder. My internal body temperature did not change. If you got closer to a fire and your blood started to boil, that would be bad. You would die, right? So your internal body temperature is 98.7 approximately on average, right? If that changed with your exterior temperature, you'd be having a really bad life. Similarly on Earth, the proximity to the sun does not affect the internal heat. Okay? What's the last one tell you? Yeah.
Fluctuating the temperature.
Sure, that tells you about variations, right? Good. And what else? Magnetic field, very good. And what else? Strength of the Coriolis effect, which influences storms and weather. So it's all three of these together, right? Tells us whether we have a magnetic field, tells us whether or not we have strong storms. And now we basically described, if I give you a planet and I just tweak these, maybe I do this in the homework, and I say, oh, I'm gonna give you slightly adjusted parameters. You should be able to tell me, I expect to see these fundamental processes there. I expect to see this much volcanism. I expect to see this much impact cratering, etc. Does that make sense? Yeah.
What's the size of the sun make a difference?
Yeah, size of the sun and distance to the sun are kind of interchangeable. For the purposes of this, we'll definitely get to that when we get to different types of stars, but we'll kind of imagine just us. And then when we move to exoplanets, that will matter a lot. Yeah.
Does the sun cool or does it stay hot? Like, is it cooling over time or no?
That's a complicated question. We'll get to that when we get to stars. Yeah. Good question. Okay. So if you know these properties, you should be able to predict all of the properties of the object we're going to look at. And of course, with any good science, with any good theory, there will be an exception, right? So we'll talk about it, and then you'll get really upset at me, probably at the end of this class, when I show you a gigantic exception. Okay? We're happy? So, everyone medium? Medium to better? I mean, this works now. Okay, so let's start with the first lecture today. This is comparative planetary geology. No one sits in exactly the same spot. One of these days, I'm just gonna remove all the chairs from this side.
No.
I know. Then people will have to sit there first when they arrive, and then I'll move it. Right. Wait. Sorry. Am I missing one? Oh, no, no. Wait. No, I did it right. I think. Who doesn't have one? What did I do? How many do you have? Just one. You have one. Oh. David, okay. Let's steal. David's and David. Yeah, we're back. 2, 3, 4, 5, 6, 7. Okay, there we go. I did it. Make sense?
What was it?
I don't know.
Like, what was your thought process?
There's 14 people, there's
Okay.
7 of them.
Oh.
Everyone should have one partner and not one of them.
Why did you just give 7 of us?
I did. Yeah, make a new friend. David, have you worked with that before? There you go, let's go! Make new friends!
Dodge start.
Look at that, look at all these people. Teamwork makes the dream work.
Yeah. we can vote.
You know.
Might start with me. What? We actually have to work together.
You're just whispering all the time.
Yeah.
Okay. This is great, I'm so happy. Let me go get 1,000 candy from the office.
There's there.
Who's the better setting up? Oh, there's no space, I mean, you're half sit, but that was a joke. Oh, you can work on this side. Oh, you have a partner on that side? Okay, who's your partner? Right there, there you go, look, great friend.
Sorry. Oh, okay.
Yeah.
Oh. Yeah. Oh. Oh. Oh, no. I was going to. Yeah. Like farther. Yeah. Yeah.
What? You think? Make some kind of.
Yeah.
Well, okay, everyone, but it's. Actually covered in switch spot either.
And it's a lot of evidence, but like, yes. It's maybe after 5 minutes. Yeah. Down enough to be
That's part one. No, the whole section, part one.
Like which one?
Alright, now you walk.
I'll think about it.
One person. Yeah, no, that's.
I'm only this way because I haven't eaten anything, so.
Yeah, that's fine.
Well, I
But I think if it's talking about.
No, lab, we're not gonna. If you wanna go outside in the water. Real life earthquake maker, earthquake up there.
Yeah. In my head, no.
So, like area.
So
I just think all
it's not like
that.
straight.
So I think her-
The thing where things like to get mixed up.
Yeah.
I wanna say. If it wasn't like if there was.
Yeah.
Only because it's.
It's not good. I choose what's true, but it's not.
Yeah, guys.
That's what.
He's right, we do the same.
That's the other thing.
Right, yeah. You know, we're going back and forth to the urban market. Correct.
You know it's not for credit, right?
Huh?
You know that these aren't graded, right?
Yeah, you know that. So we could just write like. No.
You can write mumbo jumbo. But here's the thing, they may end up being from home. Slightly changed, slightly different. And you're like, wait, I've seen this before. Did I answer it right?
Thank you.
Of course.
Yeah. Versus. Probably all of Oh, you're right. In the whole, you know, of course, to have a higher. So.
I said it's not great.
Outlier.
You absolutely get credit for it. And I look at the answers to see what everyone got wrong, and then I put that on. Yep.
Is that what all the definitions are? All the gases. Okay, so it has, they have very.
Oh. For the. In that part of the weekend, while we found the students, no. And I guess I was back.
It's a little.
Hi. Then you're filling out more gas, you have more stuff.
Oh.
Yeah. I don't think. I don't think more transport. Yeah, so you.
Well, next semester, I don't know how they come. I think, what do you want to
Yeah. I think.
Taking it the same time as multi-dimensional. I don't know, you can have either, you took 3,300, right? After 3,300?
Yeah.
If you were learning multi-dimensional calc at the same time, would you be okay? It's a lot harder. A lot harder. I think we're gonna offer after 4,000 next semester. And maybe 3,310 in the spring.
You think I'll be ready for
When are you graduating? Oh, you got plenty of time. I would take it next, not next year, but the year after.
Are we done with multi-variables?
I know, but you want to use it in some mechanics classes. You need mechanics for mechanics.
Oh.
Is 3,000 maybe? 3,100?
Yeah.
Okay, how are folks doing? Brains warmed up? No? Okay, so everyone but Kobe, let's find a good place to stop and then we'll talk a little bit more and then we can finish up. Yeah, grab some snacks, energize the brain.
Yeah. Great selection up here. Ooh, the summer, we did that.
What's that?
Yeah, there's a sound with that. Yeah, you know, sort of fire. So that's why. That's a good one.
Yeah, these are the best. By a long way. By a long way.
They're actually.
I mean, yeah, we did.
Okay, folks, you don't have to move. You're welcome to stay there. This might be your lab partner. If you made a new friend. So we're thinking about these processes, how gravity, right, how size, distance, and rotation rate affect things like gravity. Why does gravity matter? What does it float away? The gas. We're not as big and gassy. We don't really matter when you think about planetary atmospheres. When you think about the planet as a whole, like differentiation, whether or not it's big enough that the rocks melt, right? That's a result of gravity. So when we talked about differentiation, what was that word? Differentiation. What's the word differentiation? Separation by density. Very good. So what happens to the densities that are, what large densities? things that are big compared to things that are small? Yeah, what happens to the heavier dense materials? Everything goes to the middle. Right, so all the dense stuff goes into the core, and all the really light stuff is in the crust. Right? That only happens to gravity. So if you're larger, you have more mass, you have more ability to differentiate. That's that first part. This tells us about the internal temperature. The internal temperature tells us about these primary processes, like whether or not volcanism is still ongoing. Tells us about the surface temperature. If I'm close to this fire, right? The side that's facing it is going to be warm. Okay? And whether or not there is an atmosphere. And we'll talk about this in a lot of detail. So let's start with the rule of size. So you just talked about this in your lecture tutorial. There's the different planets. Hopefully you rank them like that. Right? Anyone get tripped up? Any questions about this? Okay. So when you look at planets like this, what are the things that heat a planet? The interior. Sorry, that was a good answer, but let me rephrase the question. What are the things that heat the interior of a planet? I said that the density matters, certainly. Hold on. So let me say this differently. There are three primary processes. You have touched on one of them. I mentioned the word differentiation. So you're absolutely right. That the process of moving that material around, for example, if I roll a ball downhill, I convert that potential energy into kinetic energy. The same thing is true of when objects sink. As they sink, they heat up the area around them. Weirdly enough. Okay. What are other processes that heat the planet? What is that? Friction. So does that heat the planet? Like if I take a planet like this and I put a box around it. The net heat gone up or down? If I have something like that. Yeah, that's net neutral. Yeah.
With the convection inside the metal magnetic field.
Okay, that's interesting. So we're thinking about the interior fluid. We're going to come to that thought. Is convection a heating or a cooling method? Tides. Okay, so that's something acting on the outside. That certainly will matter, but we'll talk about it later. That's not one of the three primary processes. You're right, just a little early. That's actually a really good sound. Maybe that's one of them. Yeah, impacts deliver material and they deliver mass. And that mass is really important, right? That process is called accretion. That was perfectly timed. I wish we had practiced that beforehand. And the third one is one that you maybe are not going to get. It's radioactive decay. Okay, so here are the processes that heat the planet. Okay, on a grand scale. You're absolutely right. The surface of the planet is going to matter, distance, everything else. If I light a nuclear weapon off here on the surface, that will briefly heat the planet, but not for very much. Okay. The first one is accretion. This is material. Let's say I have a very young protoplanet. Proto just means baby, hasn't yet formed. Right after it was born, all this stuff smacks into it, adding energy in the form of mass and velocity. Melting the surface, putting that new material in. Maybe it's a giant metal asteroid. Okay, what does that asteroid then do? It sinks to the core, and as it sinks, it transfers heat. Okay, so that was your accretion. Gravitational potential energy, doing the smack, providing the heat. Okay. Differentiation, already got that one. That was perfect. Okay, light stuff go up, then stuff go down. Light stuff going up is still doing what? It's net heating. Okay. Light material rising is net heating. It's drawing away of pressure and pressure. Okay. And finally, radioactive decay. This is the fun one. So if you go into a basement in Colorado, you will see something called a radon mitigation system. Radon is the heaviest noble gas. So it just seeps, just like helium. If you put it in a container, it'll just get out of the container if you wait long enough. Except radon is great because it decays radioactively. And as it decays radioactively, it gets trapped in your lungs and gives you lung cancer. Isn't that cool? That's pretty cool. Well, we're all gonna get lung. 1 in 6 of us will get cancer in our lifetime. But interestingly enough, this radioactive decay is what's currently powering the interior of the planet. So, for example, accretion happens very infrequently. You're not adding a lot more mass to the Earth. Thankfully, right? Because if that were the case, we'd be on fire. Yeah, dead. This is a great word for it. Okay. If differentiation was still going on, we wouldn't have ground, maybe. Yeah, probably still melty a little bit. What else would we not have in the interior? A core. Yeah, a core only forms after everything is separated. We talked about the composition of the core as being metal. Well, if you have rocks and metal all mixed up, you don't really call it a core. You just call it the middle. Right? Okay, so these two have already happened, and this is what's ongoing. And it's the radioactive decay from one particle going to another. I believe it's like a lot of uranium. I think early on it was mostly aluminum. It was a radioactive aluminum that was the primary heating mechanism. Kind of cool. Okay, so that's the processes that heat the planet. What are the processes that cool the planet? What's that? Radiation, good. Someone already said it. Time is not a process. It's not a cooling process, it's a heating process, but we'll get to that later. What's that? Water. No, that's a result of it being cold. Okay, let's do a quick lecture. What do they call it? Clicker question? And we'll come back to this. Which of the following are significant sources of heat inside the Earth today? Let me know when you're ready. Let's vote on 3, 2, 1. I got everyone. Okay, ask a neighbor. I got every response. So ask a neighbor, see if they have a different answer than you. And note that I said, which of them are significant sources of heat? Today. So the question is, which of them are significant sources of heat today?
Yeah, that's what it's currently yeah.
Okay, ready to revote? Yeah. Vote on 3, 2, 1. Still get a nice variety. All right, who wants to argue for their point here? Yeah.
So I think C, radioactive decay, because it wouldn't be accretion because we'd all be dead.
Right.
Differentiation wouldn't be the answer because we already have 4.
Right.
So the only one kind of by default is decay.
Yeah. Yeah. So in general, this is correct. there's a teeny tiny bit of differentiation, which is just happening at the core mantle boundary, but I didn't tell you that, so I'm not gonna blame you for that. So in fact, it is radioactive decay. This is the primary source of heat. And there's a tiny bit of differentiation. 5? Yes, 5 and 3 were acceptable answers, but you didn't necessarily know that. Okay. So what are the cooling? I heard one already, radiation. Okay, so that's interesting. The heat's getting through the surface. I like that. There's a more general term. Okay. So in general, these are the 3 methods. Okay, the first is called convection. What's an example of convection? Boiling water. Or the one I always use, miso soup. You get some miso soup and you look at the top of the miso soup. Right when it comes out, it's hot. It's convected. And it's cooling. It's bringing hot material up. Okay, hot material, so it's hot down here, it's cold up here. It rises while hot, it cools, bringing the heat from the interior out. Does that make sense? Then it has to do something called conduction. Conduction is a form of heating that you're quite familiar with. What's an example of conduction? Not me conducting like this, but conduction. What's happening?
Pushing.
No. I'm transferring heat, right, to the door. Because I'm hot, the door is cold. I feel that as the cold is coming into me. That's my perspective. Right? But the reality is that I press on this metal here, my warm body is making this warmer. And if I held my hand there for a long time, it would raise my body temperature. Another example, you're cooking. You place down a pan, you put fire on the bottom. The fire never touches your food, and yet your food gets hot. Magic?
Yes.
No. That is induction. Okay? So the metal gets hot, and then the hot metal transports energy to your food, and you eat breakfast. Okay? That is the same thing that's happening here. We are standing on the top of basically a hot plate. The bottom is being heated, not by a flame, but by the magma interior of the earth. And heat travels through the surface, right? The same way that it travels through any piece of metal that would be like a pan. I say metal, but it could be any heat traveling through solid object. One thing that you'll note here, convection happens in liquid. Conduction happens in solids, correct? And radiation happens in gas and space. Okay. Okay, so what's radiation? Yeah, or it can be any type of light. Radiation is a blanket term, and in fact, it's another example of how great astronomers and physicists are at naming stuff. So we said, what were the 3 forms of heating? Accretion, differentiation, radioactive decay. And these are convection, conduction, and radiation. That's the same word. Why are they the same word? Yeah, because when we first discovered radioactivity, is the same time that we discovered radiation. In the same process. So people like Marie Curie took pieces of cesium, which is an element, and noticed that stuff was coming out of it. They noticed 3 types of things: alpha rays, gamma rays, and beta rays. They didn't know what they were, but they were very, very, very powerful. Right? They said this cesium seems like it's doing something really cool. Turns out the three things that were coming out were gamma rays, light, beta rays, electrons, and alpha rays, which are just helium atoms. So they have the same name and they're totally different processes. Okay, they didn't know it at the time, and no one gets to rewrite it because she won 2 Nobel Prizes. Okay, so radiation here is the process of transporting heat by light. And that can be infrared, that can be gamma rays, that can be whatever you want, but it's taking heat from where it is, the source, and transporting it. Okay? Good success? Sure. Sure. Okay. Here's a question. Suppose a planet exactly like Mercury had formed twice as far from the sun. How would its internal heat today compare to the real Mercury's internal heat today? That's a picture of Mercury, by the way. Would A, fake Mercury have more internal heat? B, fake Mercury would have less internal heat? Or C, fake Mercury would have the same amount of internal heat? Let me know when you're ready. Okay, let's vote on 3, 2, 1. Okay, all right, I got it. I got a few of you. All right, what do you guys think? Anyone want to argue for their choice? I shouldn't have said that. Now no one wants to be the person who argues.
Well, I heard B, because I'm only thinking about surface temperature only differentiates, like distance.
Right.
But not-
Surface temperature was different from internal.
Yeah.
Right. Okay. So in fact, it is fake Mercury would have the same amount of internal heat, but of course the surface temperature would be quite different if it's farther away. Okay. Good. So size determines internal temperature, distance determines surface temperature. Okay. And of course, that can get a very, very complicated very quickly as soon as you add a big, thick atmosphere. For example, look at Venus. Okay. So we want to understand things like what would the Earth be like if it was 10 times bigger, but rotated 100 times slower. So think about these 4 fundamental processes and give me an example. Raise your hand. Give me an example of what would be different with one of them. Yeah.
Would be a lot more volcanism on the planet.
Okay, a lot more volcanism. Very good.
There'd be less erosion because there wouldn't be as much wind.
Okay. So yeah, so rotating slower means less active storms. So we might think less erosion. Only 2 left. Yeah.
Wouldn't have the same effect if it was the same amount.
Like impact craters, you wouldn't see it.
It would have to be 10 times bigger. Do the same impact, I would say.
Yeah. So you'd have to have 10 times as much in order for it to see it. What about the surface itself? Would it be young or old? Okay. Why would the surface be old?
Have more craters.
Okay. So you think, okay, bigger object, more craters, right? That is a very natural response. And let me show you that it's a little tricky. Because there was an answer over there that said that there would be more volcanism. And then it would be hotter inside. So even though it would be bigger, and it certainly would have more impacts overall, they would then get covered. Right, so we have to build in our head this really interesting mental model, right? Which you're absolutely right. Okay, bigger internal temperature is higher. It does get hit more often, but it's more likely to have those erased. because of the internal heat. Right? What about tectonics? What's that?
Almost none.
Why would it have almost no tectonics?
I would say. Because the lithosphere is probably very thin.
Oh, okay. Okay, so just like a soup.
Yeah.
Okay, so imagine there is a lithosphere. Okay, I'll make this justification. So, you're thinking of this example of like, well, what if the whole thing was just molten all the way through? Whole thing's molten and you have like a magma surface, then it's a moot point. You have to assume that there is some crust. Okay. So more or less tectonics on a planet that does have a crust, but is 10 times larger. Why more? Hotter move more? Yeah, that's a pretty good argument. I like that argument. I would take it. Ongoing tectonics in particular. Right? So tectonics was deforming the surface. And remember, the reason why it's deforming is because magma underneath the surface is pushing and pulling either plates or in our case, or sorry, in Venus's case, like distorting the entire surface, making it mushy. Okay? So if you have more motion in the interior, you're gonna have more motion on the chewy exterior. That makes sense? I'm trying to think of a candy that's like soft on the outside, but like a liquid on the inside. A gusher. Very good. Okay, so if a gusher, that's a great example. I'm gonna use that from now. Okay, if the gusher had motion and it was like, because you know the surface itself is sort of gooey on long time scales. It's not brittle like you think of it today. It's moving. So imagine that the interior of the gusher is rotating and it's pulling on different parts of the gusher. Okay. Okay, so we did that. This is the whole process of what you'll be able to do. Let's do another one. What if it was 2 times smaller but located 3 times closer to the sun? Raise your hand. Yeah.
Crazy high surface temperature.
Okay. Well, how does that impact the 4 primary processes?
I mean that. Well, actually, it's not really an effect of primary processes, right? That would be based on the lithosphere.
That's a good question. No.
Then smaller, have a much bigger lithosphere.
Okay, so 2 times smaller means bigger lithosphere. I like that. How does that impact one of the 4 primary processes?
There'd be less tectonics because the lithosphere is larger and everything's cooler.
Right. So now the interior is cooler, respectively. So the lithosphere gets larger. That makes it harder to deform. So there's more gummy exterior and less inside of your gusher. Right? And also less volcanism. As the lithosphere gets larger, it gets harder for magma to make its way through the lithosphere. More impact cratering? Why is that?
The surface is older, so it doesn't have time to restore.
Right, so due to less volcanism, maybe the surface is going to show more impact crater. Anything else?
I think less atmosphere, maybe a bit.
Okay.
And not having volcanoes.
Yeah, so you don't have any volcanoes for the gas, and you're so close, you have 3 times closer. How's the temperature on the surface? Hot. How's liquid water on the surface? Non-existent, exactly. So liquid water is one of our best eroding agents. That's gone. Or is there evidence of erosion on this fake planet? No. See how cool that is? Wow, that's a super useful skill, Mateo. I'll use that tomorrow in the gas station. Okay. So the primary one, and you're kind of noticing this, I ranked them, and I ranked them by importance. Okay, so we see planetary science tells you almost everything you need to know. If you're big, your interior is warm, you can do a lot with that, right? And then it's distance from the sun and rotation. And so now we can explain the surfaces. Pretty much any surface I show you a picture of, you can look at it, you can identify the primary processes, and you can tell me what you think the surface is. like what object it is, right? Okay, this object's bigger than Earth because there's not very many craters. And even though I don't see water, it looks like there's probably tectonics ongoing. So the interior must be warm. So it must be bigger than Mars, maybe bigger than Earth, right? Pretty cool. Okay. Volcanism and tectonics require internal heat. Small terrestrial planets do not do convection. So even though Mars has the largest volcano in the solar system, this basically comes from the fact that it was doing what we call superconvection in one location. So it started one cell, it wasn't doing it everywhere, and it was just spitting all of this stuff into a weak point in the lithosphere and just melting it over and over and over and over and over. Once it's melted, you can keep it going. So it created a superjet. That's why there's only like 6 volcanoes on all of Mars. One of them is the biggest volcano in the solar system, but on the Earth, for example, you have hundreds of them, and new ones being started every day, right? Okay. Erosion's the complicated one. This one is always tricky. Okay, so it requires all 3. So role of planetary size is important because as you have more volcanism, you get an atmosphere. That's the source of a lot of volcanic outgassing, right? And then you also have the distance from the sun. So if it's too close, we just talked about the fact that liquid water can exist. And if it's too far, you get what?
Oh.
It's cold. It's frozen. And frozen water, I know it's very unusual here in Southern California, but we just saw it this morning. It's called snow. And other planets have this. Other places in the US have this as well. It's pretty crazy.
Have you seen it?
Yes, I saw it this weekend. Right in my house.
That's crazy.
What? It's crazy. Okay. So this distance from the sun is really important. Because if you want good erosion, you want water. You can do some erosion, right? You get sand, you move it around with some air, boring. You can get really cool erosion if you have glaciers. So Mars has like glacial erosion of like CO2 ice. Very cool. But nothing's as cool as water. Because water makes a Grand Canyon. Now you might say to yourself, well, that's the smallest canyon system when you compare it to my Bias Marinus. There's a larger canyon system on Mars. And that's not caused by erosion. That's caused because the whole planet cracked open like an egg. You ever like made bread and then it cracks? I'll make bread. I'll show you a picture of bread next week. I'm not gonna make bread. But as the bread cools, it heats up and then cracks. Okay. And then the role of planetary rotation is also really important. As we mentioned previously, if it's rotating quickly, the storms are really violent. Okay, we'll see that especially when we get to Jupiter. Jupiter is sick. Okay, there's erosion. There's impact cratering. This one's also tricky. Okay. A planet's characteristics do not control the creation of impact craters. We assume, and I haven't showed you this yet, that impact cratering as a rate, the amount of stuff hitting you, is constant. What does that mean? That means that you assume that if you wait long enough, something will hit you. Okay. Now, if you're bigger, you would say, well, the total number of impacts goes up. And that's absolutely right. Right? Except for if you're bigger, then you're going to erase them with volcanism and tectonics. So there is a sweet spot in there, right? Where you can be larger than, say, Mars and have, like, Mars is very impact cratered. But imagine it still had some internal heat. Let's say it was larger, that could resurface it. Even though it got hit more, it would look like it had it. We're a great example. How many different craters do you know about on Earth?
Couple questions.
Yeah.
Regarding the sun and the distance in the.
Yeah.
How does that apply to time?
Getting ahead of yourself. Wait, I'll show you. I'll show you in a second. Very good question. Very good question. Volcanism here is only talking about the rocky terrestrial planets. rocks. Okay, last one. This is the geologic history of the terrestrial planets. Okay, this is the cratering rate over here. And the planets all formed at the same time, based on every piece of evidence that we have so far. All the geologic evidence, all the geochemical evidence points to almost simultaneous creation, except for a small hiccup with the Earth that we'll talk about in a little while. So the moon and the Earth have the same date, and these have a slightly different date. Which of them formed first of these? Like this group or this group? What?
I mean, Earth would be later.
Earth is slightly later because Earth and the moon, they formed, this formed from hitting this. We'll talk about that when we talk about cosmic collisions. But if we look back in the history of time, planets form over here, and the moon cools down almost right away. It's been an ancient place since like 1.5 billion years ago, or 1.5 billion years after it formed. And it's just been accruing hit after hit after hit after hit. So even when you look in a crater, you'll see craters in that crater, right? Whereas Moon and Mercury, we don't really know what happened to Mercury, but it looks old as yet.
So has the Earth been, I mean, has the moon been taking most of the, like, impact craters or hits for us then?
No. No, this is really tricky, right? So we think of the moon as like our projected older brother. But really, if you think about it to scale, okay, the size of the Earth is about this big. Okay? And then the size of the moon is about this big. Okay, so where do I put my hands in order to get the distance between them correctly? Or farther? How much farther? 35. What? More than my arms can stretch. Recall that the difference here is like a factor of 50 between their distance. If I put like this here, and I put the Earth like over here. It's a very, very poor shield because it's so small and it's super far away. So in fact, a lot of stuff. But we have a different protective layer. Atmosphere, the atmosphere. Atmosphere protects us from a lot of small stuff. And the third protective layer is that 70% of the water, 70% of the Earth is water. And that means that you just get tsunamis instead of like, explosions.
Oh, that's what.
I don't know.
I choose a tsunami.
Not so scary.
They're getting hit by a giant rock in space. At least I can just run up a hill. Tsunami goes on the ground.
See tsunamis, they're terrible.
Okay, all right, we're getting off topic here. So Mars turned off at some point. InSight did see, so we landed a seismometer, and we'll talk about seismometry. InSight did land on the surface, and it saw, I think, like 2 Mars quakes. It saw a Mars quake from something impacting the surface. So something impacted and sent vibrations, and then they found it. Pretty cool. And Venus is certainly alive. In fact, the whole surface overturned over 600 million years. And there's a great new paper that came out that says maybe it just is super squishy. I don't know.
Is that true?
True is hard to say with Venus. We cannot get to the surface and like collect a sample. We're trying to. As soon as you can land on the surface, collect some rock and understand what's inside of Venus, we will understand it so much better. We can't even scoop lava. Here, you know what you do if you were a geologist? You go down, you have a little bucket and it's filled with water. And you have this weird like metal hammer, and you go to a lava and you just grab the lava and you put it in the bucket. And then you take that rock and you can analyze what the lava was made of. So we know what the interior of the Earth is made of. You can't do that on Venus because you can't even land on the surface for more than 50 minutes before everything melts.
Why can't you just like?
That's correct. That's what we should do. But landing on the surface is really hard. We'll talk about the Venus atmosphere later. Okay. So we had this period of heavy cratering. We're going to come back to that. And ever since, there's basically a low level of cratering. And we can see this in what's called the cratering record. We can see that older material, lots of craters early on, and then less craters since. Here's the rotation rate of every planet, including the ones that are out here. Is this a video? Let's go. Okay, this was put together by someone I found on Twitter. And they also put like the basin. So did you see that one? So like this one. It's okay, I didn't even really like this thing. Oh, that even worse. Okay. So as you watch them, notice the rotation of Venus. That's correct.
Oh.
Its rotation period is 243 days. Its day is longer than its year. It's also flipped upside down. It's rotating in the wrong direction. Okay? Oops. Mercury. Why won't they just play over and over and over? What do you mean? So because we're either colonized or colonizers, we think of the US and Europe as the north part of the planet. And so therefore we think about the rotation from the perspective of the North Pole. Okay? Here, all of these are seen with reference to the North Pole. So you're absolutely right. Maybe Venus is the only one spinning in the right direction, but we're all spinning in the wrong direction.
That is the outlier.
But it either way is an outlier, at least within the terrestrial planets. You'll notice that here, Mercury is spinning in the same direction that we are, right? Like that, in the same direction that Mars is. And look at those numbers, huh? 23 and a half, 25 and 0.2. Look at these periods, 23:56 minutes. This is the day on Earth. That's almost the same as Mars. Coincidence?
Maybe not.
No, yes. The answer is yes, it is a coincidence. Do not read any more into those numbers. Okay, that is a coincidence as close as there is one. What about this? You ever heard of that? Series. So this is not like your favorite show. This is series. This is a planet, dwarf planet that lives in between Mars and Jupiter. It's large enough that it's round. It's large enough that it has water ice under the surface. And notice that it's very similar to Mercury in color and rotating in the same direction. Look at Jupiter. Jupiter's fun. I want it to play over and over. Look at how quickly Ceres is spinning. Look at how close Jupiter's spinning. Oh, look, it is staying. All right. And then something else is happening out here. Who knows? They're drunk. Okay. So I'm not going to do that. The geologic history of the moon. All right, whatever. Impacts were recorded for nearly the entire history in the highlands. Volcanism, the only form of volcanism we see on the moon is Mare, or Maria. Tectonics, you see small like wrinkles and cracks in the surface. And there is no erosion in the way that we typically think of it. However, there's tiny things called micrometeorite sandblasting. That's when a small thing hits, like blows dust away. But those footprints on the surface of the moon will be there for 50 million years, probably. Okay, dead. Mercury, similar. It's got more complicated geology. So it has more spaced impacts than the moon. It has this really cool feature called the Caloris Basin, which looks like you hit one side like this. Imagine that this is planet Mercury. You hit it on this like big basin here, and then on the other side, you melt it. Yeah, really cool. We can maybe show that on Wednesday. Volcanism, not a lot. There's some like lava plains, some volcanic vents, potentially. But again, this thing was mostly core, very little mantle. We haven't described why that is. Tectonics, lots of aligned ridges. The whole planet shrunk, just like we were talking about red earlier, the form of like shrinking, cracking. And there's some interesting evidence. I don't know where this sits so far. like icy substrate that melts and then stuff falls in where the ice was. Melt, the ice goes away and it falls in like sinks in. Right? Yeah. Dead as a doornail. Okay. Venus, alive or dead? Very alive. Too alive. There's about 1,000 craters total. And that's where they are. This surface of Venus is something that you've probably never stared at before in your whole life. Isn't that crazy? It's our nearest neighbor and you don't even know what the surface looks like. Wow. But Mars, you kind of like have an intuitive sense for, or no? Just red, right? Just red. And little aliens that are green, right? Yeah.
Maybe blue.
Navy blue. So yes, there's absolutely no evidence that Venus is dead, very much alive. We think that there's lots of volcano today, likely active, likely spewing out gas. The thing is there's probably no erosion. Why is that? Barely rotate. The surface winds are gone. There's no surface. There's oppressive heat. Okay, active. Yeah.
Has there been anything that's like landed on Venus? Like in
Yeah.
terms of like from like
Yeah. Okay, that's another thing I'll put in the slides for Wednesday. So when we send things to Venus, we know they're going to die. And so we send them with a very quick, like, hey, say hi and tell us. So we tell them to take pictures. Send the pictures back right away. And what we do is we put 3 different colors, like a green, a red, and a blue. And we know what those look like when we sent them. And then we land them on the surface and they take a photo, but it's looking through basically sulfuric acid in a lot of cases. So it looks very yellow. And then we convert that color, get what it really would look like to us. And cool. Okay. I don't have time for this, but I really want to get to this point. This is the geologic history of Mars. You see that the northern hemisphere is much younger than the southern hemisphere, and I'll show you this on a map of Mars if you're curious. We think either there was a giant impact that formed the entire northern part of Mars, or that there was a massive ocean. But either way, the northern hemisphere is much more resurfaced than the southern hemisphere. So we call it the northern lowlands, because they literally are lower, and the southern highlands. We saw that there is the biggest volcano in the solar system, that's Olympus Mons. That white color is not ice. This is altimetry data. So this is fake coloring, I apologize. Here's the largest canyon of the solar system, that's Valles Marineris, again, from altimetry data. We've never flown like this to take this picture, but it would be sick. If you go to like a planetarium, you can like fly into this. They have like 3D models of the entire topography and fly around to them. So ask the dean if we can buy a planetarium. Okay. And there's lots of erosion. We saw evidence of erosion. We saw dust devils. Alive or dead, Mars? Maybe on its like life support. Okay, so this is an example of how it's on life support. This is a Mars quake. Good. Okay, we're gonna see more Mars quakes, or more earthquakes. No, we're not gonna see. Go away. Okay. Geologic history of the Earth, alive or dead? Okay, move point. We're gonna move past this. Let me show you this object. Okay, don't say, if you know what this is, do not say it, please. Do not say it. Okay, it is soup. No, I'm just kidding. So as you look at this surface, I want you to tell me what types of features you see in terms of our planetary processes. Impact cratering, tectonics, volcanism, etc. Yeah. Do you see volcanism?
I feel like, maybe not like volcanism, but like, the vents. Is that-
Vents.
Yeah,
Like this?
yes.
Yeah, this could be venting. Yeah, maybe it's volcanism. Anything else? What's that? Different colors. What are the colors we see? Orange. Is that normal for a planet? Kind of weird color. Venus has that color. Right? Do you see cratering? Where? Like here? Where do you see the craters?
Right next to like.
Here?
Like. Yeah.
Okay, alright. Anything else? Yeah.
If there's volcanism on the planet, then there's gotta be tectonics that gases that come from it.
Okay, gases come from outgassing and volcanism, but tectonics don't necessarily mean outgassing. There might be tectonics here. Do you see evidence for it though? For tectonics? Do you see like a ridge or like a mountain or like
Not at the top of center, maybe.
up center, like here? Maybe, okay. Okay, so what would you assume based on the planetary processes? What do you think about the size of this object? Huge? Pretty small? Big? Raise your hand for big. Raise your hand for small. Okay, does this have, how close is this to the sun? Close to the sun? Far from the sun? Okay. What's the rotation rate like? High? Low? Okay, anyone have a guess what this object is? The leaf?
I think it's Io.
Okay, raise your hand for Io. Okay. Anyone else have a guess? Utah?
Yosemite?
Yosemite? Raise your hand for Yosemite. Okay. You mean Yellowstone?
Yellowstone, there we go.
Yeah, Yellowstone. Raise your hand for Yellowstone.
It was one of those.
Okay. Any other votes? No one likes Venus? Ohio? No, this is not Ohio. Okay, in fact, it is Io.
Ohio?
Ohio.
Jupiter.
So even though I just told you all of this stuff about terrestrial planetary geology, we are going to now apply it to ice, because ice and rocks are the same thing but different temperature. So we will use all of this same material when we talk about the icy moons of the outer solar system, which we're going to throw in on Wednesday. We're going to talk about Enceladus. We're going to talk about Io. We're going to talk about Europa. And we're going to talk about the fact that their interiors have liquid water, which is acting like magnet. Pretty cool, right? Okay, so that's it for today. But you have this is Io.
Oh, sorry.
We have a lab. You can take, sorry, I apologize for going over. You're gonna take like 10-15 minutes, and then we'll jump into this. Feel free to snack, feel free to go to the bathroom. Yes, please.